Assalamualaikum and good afternoon, everyone. I'm here present to give a presentation on our FIP, which was design and fabrication of soft hand with flexible sensors. My group mates are engineer Tanveer Ahmed, engineer Habibullah, and myself. Our project was supervised by Dr. Afaq Panzul, and our co-supervisor was engineer Umar Randhawa. The table of contents are as follows, which are introduction, literature review, problem statements, aims and objectives, methodology, results and discussions, and references. Introduction. Annually, 15 million people worldwide suffer a stroke. Of these, 5 million die, and other 5 million are left with permanently disabled hand, placing a burden on family and community. In United States, 41,000 people are registered have had their hands or entire arms amputated. A trembling hand in old age is when an elderly person's hand shakes or trembles involuntarily. This can be due to natural aging, medical conditions like Parkinson's diseases, and other factors. It can make tasks like holding objects and writing more challenging. A prosthetic limb can effectively improve the quality of life of those who have lost limbs. So the evolution of prosthetic technology went from using a wooden or leather prosthetic to metal casings to rigid types of robots and now the soft robots. So the prosthetic hand can be made from either rigid materials or soft materials. The rigid materials we know as they are hard materials which we normally see in our day-to-day lives. The soft materials can be further classified into tendons, SMAs, and pneumatics. So, soft prosthetic hand. A soft prosthetic hand is adaptable to environment. It is safe to use. It is versatile, robust. It has an adaptable degree of freedom. It is flexible, lighter, and less power consuming. Figure 9 is an example of a rigid prosthetic hand. Figure 10 is a figure of soft robotic hand, whereas in rigid prosthetic hand needs a well-defined environment. It is used to do repetitive tasks. It is unsafe when it malfunctions. It is less flexible. It is heavier and more power consuming. So the comparison between soft and rigid. The degree of freedom in rigid is very little, where it is infinite in soft robotics. The dexterity of the material is very low in rigid, whereas it is very high in soft. The working environment needs to be structured in rigid, whereas it can be structured or unstructured in soft. Manipulatable objects. The rigid robot can mostly be used for objects of fixed size or variable within a specific range, whereas soft robot can be used to manipulate objects of variable sizes. It is very dangerous to use a rigid robot when it is malfunctioning, whereas it is comparatively safe to use a soft robot when it malfunctions or in normal times as well. So the soft robot can be distinguished into SMAs and tendons and fluidic actuators. So what exactly are they? There are three different types of parameters from which we can make a soft robot. The tendons use electric motors. The shape memory alloy use thermal shock or electric shock to actuate. And the fluidic actuators use pneumatic pumps or hydraulic pumps to actuate the soft robot. So the advantages of using a tendon-driven actuators is that it produces a very large bending stroke, whereas the challenges are that they require external motors. Whereas shape memory alloy has high elastic modulus, high conductivity without a need for external heater, whereas it has slow response, hysteresis loss, and requires a very high current. The fluidic actuators produces a very high generation and large bending stroke as well. But the challenge is that they require external pumps and which are bulky and heavy. So these three are the main, not main, actually some types of some types of parameters which we use to design our soft actuator. So we have to decide our application and then use an actuator accordingly, as all of them have challenges and advantages. So why have we used pneumatic actuators? Because it has high grasping, infinite degree of freedom, high dexterity, lightweight, cost effective, high speed, high durability, and no overheating issue. So it comes, what is the problem statement? Current soft robotic hands lacks precision, dexterity, user friendliness. They also miss out on the benefits of advanced technology, limiting their overall use. Improving these aspects is crucial for enhancing the performance and usability of soft robotic hand in various applications. So, the aims and objectives of our FIP was to design human-inspired hand actuator. Number second, to embed a sensing feature in the hand actuator using flexible sensors. Number third, to implement an application for a rehabilitation purpose. Number third, to measure the performance of the design. So, in order to make in order to make a smart hand, we have to have sensors. So we went through multiple sensors. First, we went for PSFS, then we researched FOSS, and then we landed upon piezoresistive. BSFS is a bimodal self-powered flexible sensors. Its working principle is based on triboelectric nanogenerator and giant magnetoelastic effect. Its construction usually comprises of a conductive film, which is a magnetoelastic conductive film, and two metal coils, liquid metal coils packaged together. FOSS is a fiber optics shape sensing. It works on the principle of optical fiber domain reflectometry. It uses lumen cofolds, Teflon rods, caps, and it is made in a decast in a vacuum chamber. Number third one that we landed upon was piezoresistive. Piezoresistive, as we can see from the name, it is made of piezoelectric material plus resistive material. It uses change in electrical resistance to measure the pressure. It can be made from different piezoelectric materials with different metals alloys. So the characteristics of BSFS is that it can precisely detect and distinguish touchless and tactile models. The response time of it is 10 milliseconds. The touchless signal provide valuable insight into object shapes and materials compositions. Its accuracy is up to 97%, whereas FOSS can detect bending and twisting along the entire length of the sensors with sensor measure of every zero point 0.8 millimeter, enabling high fidelity full 3D state estimation. The sampling rate is up to 250 Hz, does not require knowledge of the mechanical properties. The piezoresistive is simple to construct, it's durable, it has a higher maximum operating temperature up to 200 degrees Celsius. So the advantages and disadvantages of all these sensors. BSFS is useful to describe complex objects. It can be used for precise manipulation tasks and the capacity to interpret and interact with the physical world. Whereas its disadvantage is the algorithm's inability to describe unfamiliar objects. The system can only perform multimodal perception and description of objects it has been trained on. It cannot describe objects outside its training set. The advantages of using fiber optic shape sensing is that the fiber optic cable is compliant with the bending radius of curvature as low as 10 millimeter, and it has the ability to accurately detect the shape of the tip and tip position of the soft actuator, whereas the disadvantage of the fiber optic shape sensing is that it only gives us finger size model for the actuator and is an open loop shape sensing system. The advantages of using a piezoresistive sensor is that the piezoresistive strain gauge has the advantages of being robust, their performance and calibration is also stable over time. The disadvantages, whereas, is that they consume more power than some other types of pressure sensors, and this may mean they're not suitable for battery-powered or portable systems. The feasibility of using all these sensors. We did not use BSFS because we did not need a self-powered sensors as it already uses tanks, and the unavailability of inkjet printers from which we were unable to print our coils. And we also did not use fiber optic shape sensing because its size is 10 millimeters and the channel tunnel of the finger is only 2 millimeters, hence we were unable to use that. And we use piezoresistor because they can be easily embedded into a soft robot. They are compatible with EcoFlex material and they are able to give robust results. So the methodology or fabrication of making a sensor. Now first we created our mold, which we made which we made the which we made in SolidWorks and then we 3D printed it. Second, we used a mixture of EcoFlex and graphene and we poured it into our mold and then we embedded it on our hand to collect data. The materials that we used were graphene nanoplatelets and second was PDMS. We did not use PDMS, we actually used EcoFlex Part A and Part B. Sample preparations. PDMS curing agent solution was mixed with the desired quantity of graphene nanoplatelets. The mixture was continually and mechanically stirred for zero point 0.5 hours, which is equivalent to 30 minutes. And we stirred it via a magnetic stirrer, which was then sequentially added with the PDMS base agent at the ratio of 10:1 to the PDMS curing agent and mechanically stirred for zero point 0.5 hours. To obtain GNP/PDMS nanocomposite solution, the terminated mixture solution was degassed for 30 minutes. The resulting GNP/PDMS nanocomposite solution was poured into molds and cured at 100 degrees Celsius for 2 hours. The rectangle film samples with area of 10 by 40 millimeters square and thickness of 1 millimeter were prepared for sensing tests. Both end sides of the GNP/PDMS nanocomposites were coated with CU electrodes to reduce the contact resistance before measurement. This is the visual representation. In this, we are adding GNPs to our PDMS curing agent and then we are stirring it for a little while and then we are adding our base agent into this mixture and then we are getting PDMS/GNPs nanocomposites. So this is our end results of this just the sensor and it is used for finger motion detection. The experiment shows that the flexible piezoresistor sensor was made up of 3.58% of the nanocomposites. It can reliably detect and respond to finger motions, exhibits consistent performance over multiple cycles of bending, differentiates between different bending amplitudes, indicating its potential for detailed motion recognition. These capabilities suggest the sensor's suitability for application in artificial skin, human-machine interaction, and wearable motion sensors. This is the graphical abstract of our sensor. In this, we added GNPs with a PDMS solution to get nanocomposites, and then we can see the strain graph and the pressure graph, which is changing when we are putting pressure on our sensor. And then to actually make the whole hand, first we had to make it in simulation. For that, we used ANSYS software. ANSYS software is relatively difficult to use, so first we made the palm and the molds and the whole actuator in SolidWorks, and then we sent that STEV file in ANSYS to simulate it. For the molds, we use SolidWorks, as you can see here. That is the mold for the palm, and this is for the actuator, and this was the actuator for ANSYS that we actually sent in ANSYS to see the deformation of the finger and the deformation of the complete hand. So the methodology and fabrication of the hand was that first we printed out our molds and then we pour a mixture of EcoFlex 0030 and then we got our whole hand and then we assembled it. So the working principle of our hand was a pressure gas source and a pressure regulator, which was providing pressure to the pneumatic control valves, which the pneumatic control valves were connected with the solenoid, and the solenoid was actually giving the pressure, controlled pressure, which we were controlling from our control board and a host computer to the soft actuator, and it was bending. And the pressure transducer transducer was on the soft actuator, as it can tell us how much pressure we are putting. So we did some results. We did some simulation. We did almost 4 trials on two different pressures, 30 kilopascals and 25 kilopascals. This was a result of first trial. In this, we can see that it's bending, but the main point is that the maximum it can bend to sustain the pressure is 0.0598, whereas in trial 4 at the same 30 kilopascal pressure, the maximum pressure that the finger could sustain was 0.06252. The difference between both is that we changed the chamber sizes. We changed the chamber sizes, which ultimately gave us a different results in simulation. So from this, we concluded that trial 4 was more suitable for us to use as it can sustain more pressure. So this was our first trial and fourth trial at 25 kilopascal and 30 kilopascal. In the 25 kilopascal, we can see that our first trial went to maximum 0.05 and our fourth trial went to 0.06. Whereas at 30 kilopascal, we can see that our simulation and the finger was able to sustain 0.0598 maximum, and in the fourth trial, we can see that it can sustain 0.068571 maximum. So these were the graphs that we got from our simulation. These are graphs of deformation versus time and stress versus strain. The dots showing there are of different trials that we did. The first dot shows our first trial, the second trial, and the next one is third, and the last one is fourth. So the more deformation it can sustain and the more pressure it can sustain, the better the hand is for us. And the more strain and stress it can sustain and the bending of the finger in a required direction, the better will be our finger and hand to use for daily life. So this is the simulation of the whole palm that we did in ANSYS software. We can see in total deformation versus time that it is deforming quite a bit. And the second graph is of pressure versus the total deformation, and it is sustaining almost 30 kilopascal as we intended it to do. So this is a video of the simulation of the hand. The maximum the tip of the finger is sustaining is 0.092144, which is quite a bit for what we are doing. So this is the GUI interface that we designed to easily use our hand or different tasks that we intended our hand to do. So the different tasks were grab a bottle, grab ball, do exercise, which was our objective as a rehabilitation, and then start button and a stop button. So the hardware video of our hand.
एक मिनट बोतल लेकर आऊँ
In this, we are entering of till how much time the hand should hold the bottle. As you can see, it's able to hold the bottle for the allotted time that we defined in the program. So our hand is working is that we are using a host computer which is giving commands to the control board, and the control board is giving commands to two pumps, which are positive pump and negative pump. The positive pump is used to for hand to bend, and the negative pump is used to suck out all the pressure and return our hand to its rest position. The pumps then are giving pressure to 5 solenoid valves. The 5 solenoid valves are connected with 5 fingers, as not every finger is given the exact amount of pressure so that they could work as a whole system rather than separate different separate different fingers. And these were the results of our sensors that we made. As we were straining it, the resistance was changing. With the change in pressure, so these are the references and image courtesies. Thank you for watching.